Welcome to this presentation on exponential of a matrix. My name is Kannan Moudgalya. In this presentation, I will first motivate why exponential of a matrix is required. We will define it, derive an expression, and then we will also obtain the derivative of exponential of a matrix. Remember, we work with continuous time plans of this form x dot equals fx plus gu, and we discussed the need to make it understandable to the controller, and we agreed to discretize the plant model. For example, we need to convert the plant model into this form where n is given by the sampling instance. We need the concept of an exponential of a matrix for this discretization. This is what we have. How do we go from continuous time plant to discrete time plant? We do that using the exponential of a matrix. If the plant is naturally discrete time, of course we can skip this step. So let us start with discretization of x dot equals fx plus gu. These are all continuous functions of time, and we also assume f to be square and constant. This method will work only if f were constant and square. We will define exponential of the square matrix f into t as follows. Recall that this symbol means defined. Alright, this is equal to I plus ft plus 1 by 2 factorial f squared into t squared, 1 by 3 factorial into f cube plus t cube, and so on all the way up to infinity. And notice that this is identical to the scalar case. In other words, if f were a scalar, this is identical to the expression we would have used. Okay, let us give an example for this. Let f be a 2 by 2 matrix as given here. So this term can be calculated. Next we need to calculate the second term. So for that we need f squared. So f squared is given by multiplying these two together. When we multiply, it is easy to check this, you get this. Okay. So similarly one can calculate f cube and so on and substitute in exponential ft. So exponential ft is identity plus next term this into t. So this has to be multiplied by t. So we have 0t, 0 minus t plus 1 by 2 into f squared into t squared. So t squared can go inside and we get this. Similarly, the last term can also be obtained. I would want you to verify that you get this term. Let us now total up. You can see that 1 term is given by 1 only because it is 0 from second matrix onwards. Let us do it for here. You can see that this is equal to t minus t squared by 2 plus t cube by 3 factorial. Okay, and of course the 2 term is 0. What about 2? One can see it is 1 minus t squared by 2 and minus t cube by 3 factorial. So you get this, and this can be simplified. It is easy to arrive at this expression. Okay, I would want you to remember this. Later on we will have one more example of this f. You may even want to note it down on a piece of paper. This is f and this is exponential ft. It turns out that for actual computation of exponential ft, the method that we presented in the previous slide is not used. Instead, an efficient algorithm is used in computational systems such as Scilab. You may be interested in seeing this paper, 19 dubious ways to compute the exponential of a matrix 25 years later. It is a classic paper, you may want to get hold of it and read this paper. Next we need the concept of derivative of exponential of a matrix. We have exponential ft's expression here, let us differentiate it. Okay. So differentiate both sides with respect to t, and let us differentiate one term at a time. So this will be 0, remember f is constant, so derivative of t is 1, so you have f here, this becomes 2t, this becomes 3t squared, and simplifying we get this expression f plus f squared t plus 1 by 2 factorial. Remember this 3 cancels 1 3 here, so we get this expression, and f is constant, f is a common factor for all of them. Let us pull it out. So I have pulled it out on this side, and whatever is inside is nothing but exponential ft. So we have exponential ft into f, and instead of pulling f on this side, I could have pulled f on this side, left hand side, and if we do that we get this expression. As a result, once again it behaves like a scalar. So identical to the scalar case once again. Okay, how do we use this? We will see that in the next presentation. To summarize, f is square and constant, exponential ft is defined, derivative of exponential ft is obtained. This brings us to the end of this presentation. Thanks for joining. Goodbye.